I'm afraid I know even less Korean than my colleague Kumagai-san, so I apologize. Thank you very much for inviting me here today. I'm very happy to visit from Boston, Mass. Today I'm going to tell you how process simulation and other tools have evolved to the next generation and what current practice is for using process simulation to effectively and efficiently design plants. So I'm going to start with a walkthrough of a typical process modeling activity. We're going to look at the revamp of a VCM process. And I'm going to use that example just to show you what a typical workflow is. And in the next section, I'll talk about the actual engineering project workflow based on projects that we've done at Aspen Technology. I'll follow up with some real-world success examples to tell you how this technology has been applied here in Korea. And towards the end of the talk, I'll make some suggestions about where universities can help advance the technology for the future. This diagram shows the workflow of an engineering project. The blue boxes represent the core process engineering workflow. The green boxes show where we can subsequently use process models to help plant operations. So typically, we start with process performance modeling and analysis. And as Dr. Kumagai showed, that's not limited to simulation, but could also be any kind of numerical analysis, equation solving, basic understanding, lab work, and so on. You need to do fundamental research to understand any new technology. But eventually we need to capture that knowledge in a convenient framework, and process simulation is such a framework for capturing our understanding of the chemical process. From that modeling, we can grow out and look at equipment design, equipment cost, equipment performance in dynamics, and eventually develop the detailed front-end engineering package, a very detailed cost estimation, and go out into the build. So I'll look at this step by step. Consider the following example. Here I have a section of a vinyl chloride monomer process up here on the right side. And you'll notice that in this process there's some reaction steps. The reactions occur at high temperatures, so they require preheating. The subsequent distillation to separate the product from the byproduct occurs at lower temperatures, so it requires aftercooling. So in this kind of process, we preheat, react, cool down. There's an obvious opportunity there for heat recovery. So a process engineer may look at this process and think about another option, another conceptual process option. So here we recycle the reactor product back to exchange heat with the feed to capture energy. So this is a somewhat trivial example. We could look at that and a good engineer would see that immediately. But in a large-scale facility where there's many interacting equipment, it's not always obvious where these opportunities lie. So there's software such as heat pinch analysis and distillation sequence analysis that help to identify these kinds of opportunities in a very complex chemical process. We can also use a process simulation model like this to study other types of process configurations, maybe reactors in parallel versus series, for example, to look at the optimal operating conditions for each process. Typically, a process simulator allows you to carry out multivariable optimization studies considering the constraints on the process, so that we can find the best condition for each piece of equipment and also the best size for each piece of equipment. We can do sensitivity studies of the process to find the important variables so that we have a better understanding where to focus the design work. And we can identify bottlenecks, especially important for revamping existing plants. So identify where which item of equipment is currently bottlenecking you, and evaluate what other equipment will be the bottleneck in the future if you revamp a particular piece of equipment in the plant. Now, as the design matures, and we come up with the concept that we're satisfied with, we need to start sizing that equipment, designing the details of the heat exchanger, compressor, and so on. Now, one major paradigm shift in the engineering software arena is the move from different sets of tools, separate tools, into a more integrated approach. So, for example, with the current Aspen 1 engineering suite, we have detailed heat exchanger design tools, like you see here, tightly embedded into the process simulation. So in the past, where a process engineer might hand off this design to a mechanical engineer to design the exchanger, the current best practice is to bring this work process forward into the workflow to make the overall project much more efficient, to reduce the man hours and the engineering time to design the new process. So with these kinds of detailed design tools, we can answer an additional set of questions, such as what size of equipment do I need, what type of shell do I want to use. I can look for operational problems like vibration. I can get a cost estimate of the equipment, and so on. So we've proposed a new process, but any type of change like this involves trade-offs. So we've introduced some additional capital equipment into the process. Will the cost of that capital equipment be offset by the energy savings? We can use cost estimation software to analyze the economic performance of the existing process as well as the proposed alternative to help guide decisions. Because cutting energy may not be the right solution if it leads to substantially higher capital costs. So with a cost estimation software, we can answer questions like, how much higher is the net capital cost for the proposed alternative? What will be the difference in the operating cost? What will the cost flow look like over time? Where does a payback occur for this project? How do raw material and energy costs impact the proposed project economics? I've been in this business about 20 years, and I've seen many revamp projects fail because before they're finished, the economic situation changes. The price of oil goes up, the price of oil goes down, and suddenly a project that looked great 6 months ago is no longer attractive. So doing this kind of financial analysis is very important also for identifying the risk of doing a revamp, a particular type of revamp. And again, this is a paradigm shift in the engineering software, in that before, the process simulation and the cost estimation were two different groups of engineers. We have cost experts in one department, we have a process simulation department somewhere else, and someone throws the design over the fence. The software is evolving today where we can directly send a process simulation at the push of a button and get a quick cost estimation. So we've eliminated the silo between the two types of experts, making the overall engineering workflow much more efficient. Now, we've determined that the new design saves energy, that it's economically attractive. That doesn't mean that we should go ahead and build it in the plant. Maybe the new design is not safe. Maybe the new design is hard to control, hard to start up. So to understand the overall impact of that proposed change, we really need to consider the process dynamics as well as the steady state performance. So the current practice today in industry is to use dynamic simulator to really study the way the process behaves. Now, to do that, we need to introduce a higher level of detail into our models. So an engineer may add valves, holding tanks, as well as a control strategy, as you see in the lower diagram. Again, since the 1990s, the paradigm has shifted away from two different types of software, and we're working today to merge the steady state and dynamic software into one package so that it's easier to go from the steady state design into the dynamic design. Now this project I showed you is a very simplified example. In a real process revamp, there may be dozens of scenarios like this that are under evaluation. And of course, each scenario is much more complicated with more equipment involved. Further, this process line may just be part of a complex. It interacts with other equipment in the total chemical complex. It interacts with the utilities. So we're never working in isolation. Usually, we have a project like this. It's involving dozens of engineers in different disciplines. We have chemical engineers designing the process, mechanical engineers designing the equipment, instrumentation specialists, process control experts, and so on. Today, best practice in industry is to use engineering database such as Aspen to allow users to work together concurrently. So this is a type of groupware that keeps the process design in a way that allows all the users to see the current state of the design. So it collects the process flow diagrams, the equipment list, the data sheets. It makes it very easy to generate a report, to see the design, to generate all the data required to hand off to vendors, to communicate with the fabricators and so on. These types of engineering databases are closely coupled to detailed cost estimation software like K-Base, so that we can take a process design, preliminary P&ID for example, and work up all of the detailed costs associated with that process. These types of tools allow us to answer questions like, what is the best utility to use for the plant? Should we use steam? Should we use hot oil? Should we use compressors or fans? Which one is more cost effective? What's the cost breakdown of the process? Because maybe we don't get approval for the full revamp. We might want to take a smaller part of the project and execute that. So with these tools working together, it's very easy to work out many scenarios to be prepared for different real-world conditions if the energy market changes or if management limits the amount of resources available. Now in the past, process simulation was limited mainly to the design phase, and companies may pick it up later if there's an operating problem in the plant or if they're going to revamp. But unfortunately, it's been many situations where at the end of the design, at the end of the retrofit, the process model is put aside and we no longer get value from it. But in the past several years, leading companies have started to take a new approach. They continue to keep the process model alive, up to date with the plant, and use it as an operations decision-making tool. So for example, there's a tool, Aspen Simulation Workbook, oops, wrong button, which allows us to link a process model to process data using Excel as a middleman. Now there's several benefits here. Process simulation is a rather sophisticated tool. There's a lot of forms, there's a lot of input and output that needs to be understood. So typically this is used by process engineering experts. But for all the process engineering experts, there may be a much wider group that can get benefit from the simulation model. Remember, the simulation model captures knowledge. We should put that knowledge in as many hands as possible. Tools like this workbook that allows me to link the model to Excel makes it easy to distribute the model to a much wider group of people that are not simulation experts, maybe operators, engineers in training. Even in the business departments, we can use models to help planning decisions for planning and scheduling. So many companies today are using models to look at the day-to-day operations and also to track the changing state of the plant. For example, we can look at the fouling factor, which is easy to calculate if you have the temperatures measured around the exchanger. And we can track how the fouling factor changes over time and make decisions about when to clean the exchanger. Someone in the operator may look at a model like this to run cases to decide how to get around the current operating problem. How much should I increase the reflux ratio to get the temperature back into spec? So these types of simple interfaces allow you to continue getting value from your models after the plant is built. These process models are also useful in other workflows. So today, many companies are using Excel connected to process models to generate reports, to do additional sizing calculations, using their own design programs, many of which are also written in Excel or in programs that are linked to Excel, and to do further analysis using Excel. So that's a bit of background on the engineering workflow. I'll spend a few minutes talking about a typical project. I'm going to use, in this case, an ethylene revamp. Now, ethylene revamp is known for being a very high capital cost project. Traditional approach has been to identify the limiting equipment and scale up all the limiting equipment by a fixed factor. That's not always the best approach. That tends to lead to over-design. So current best practice is to use the integrated approach. Aspen Tech has been using this approach for over 10 years, and we've done a number of successful revamp projects based on this approach. So let me show you that. This flowchart shows the integrated design approach. Let me step through. In the first step, we developed a process simulation model. Now this is a screenshot of an actual ethylene plant model, and many of these boxes contain models inside them. They're hierarchies. So you can see a real-world model is actually quite a bit more complicated than the simple example I used earlier. So we start with a predictive process simulation. The first step is to match the real data, to match the plant. Once we've developed the base case models, we can optimize the process, and we can look at alternate designs. The next step is to use equipment design tools to find the current operating point and to identify the upper limit of the equipment. It's important to use actual performance data when doing this kind of modeling for revamp. Next, we need to use conceptual technology like heat exchanger network design and distillation sequence design. So from this kind of pinch technology, the goal is to eliminate the wasted energy between the heating and cooling duties. So we come up with a net savings of both process heat as well as process cooling. This also provides us a way to unload the process so that we can use a lower size equipment to reach the same capacity. It's also important in these kinds of retrofit studies to work directly with vendors, because often vendors have their own ways to retrofit the equipment. And working with the vendor, we can find what the constraints are. There's always a certain point where you're going to have to go to the next higher size of equipment, and the cost will go up substantially. So we can design our retrofit around those kinds of constraints. And as a result, we can find the overall lowest cost solution. This shows the typical results of such a revamp. The traditional approach, where you scale up all the equipment equally, you end up with a much higher capital cost for a given capacity increase. With the integrated approach, we can have the same capacity increase at a lower capital cost, or higher capacity for the same capital cost. I'll show you a few examples of how this has been applied here in Korea. One example is the Korea Petrochemical Company. We did a revamp study with them several years ago. And as a result, we achieved 15% higher capacity at a much lower investment cost than they were quoted by engineering companies. And you can see the quote here, KPIC is pleased with the results, not only because we delivered what they wanted, but also because as a result of process simulation, their engineers became much more familiar with the behavior of the process. So there's some very important spin-off benefits of this kind of engineering project using process simulation and other tools. Another example is a Samsung Total aromatic facility. In this plant, the goal was to reduce the overall energy cost of this facility. This is a mixed aromatics facility. To meet this objective, we applied process simulation using Aspen+. We applied a heat exchanger pinch analysis, distillation sequencing analysis, and this also involved thermal integration with another process unit. So the process study expanded beyond this particular unit into the adjacent units. As a result, 12 of the suggested projects were implemented and saved Samsung Total $12 million a year, $12 million USD a year, which was a 20% savings in their energy cost. And this is before the high gas prices. So in today's situation, this would have been substantially higher cost savings in energy. A secondary benefit was they improved the product area by optimizing the conditions of the plant. In one third example, and this is a little closer to my area of specialty, which is a polymer modeling. We worked with Hanwha Chemical to model their tubular LDPE process, low-density polyethylene. In this particular situation, they had made some changes to the plant, and as a result, they were unable to return to the capacity they once ran the plant at. So, in order to understand what went wrong, they developed a process model with AspenTech, and then they subsequently used that model to re-optimize the process conditions around the new equipment. And they were able to raise their capacity by 7 to 10%. Further, they had a much better understanding of their process behavior, which they could apply to the next plant they designed. So just to follow up, I showed today the state-of-the-art of the current process modeling, how it's moving from separate tools into an integrated workflow. There's still a lot of room for improving. I just want to touch quickly on some of these emerging areas. In the past, the process simulator was developed around a wide database of engineering knowledge for pure chemicals and for petroleum. But in the current situation, there's many new emerging technology areas like biodiesel, the hydrogen fuel cells, and new coal technology, for which there's not much published data or much understanding in the industry. Universities could really help the state-of-the-art by doing some pure research in these areas to identify kinetics for coal gasification, characterization of coals, of tar sands, supercritical carbon dioxide, amine systems for gas sweetening. There's still plenty of room for research in these areas. And also very important in the future is the use of a biological feedstock. As more companies move towards green materials, such as polylactide polymer based on fermentation products, ethanol for gasohol and so on, there's a stronger need to start modeling these types of biological fermentation processes. So again, pure fundamental research to help us characterize fermentation process is very important for the future of process design. Another trend that we see in our customer base, especially in Korea, Japan, North America, and Europe, is the companies shifting away from commodity production and moving towards higher value materials. Specialty polymers, specialty chemicals are growing in these areas as the commodities move into China, Brazil, Russia, and so on. So there's a strong need to have fundamental research to find the physical properties, the reaction kinetics, and the other background data that we need to develop simulation models for these types of processes. So I'd like to thank the ISAHE again, and if there's any questions, I'd be happy to answer questions during the breaks, or if we have a few minutes now. Thank you.